this module, you will learn about the effect of change in temperature on equilibrium. Temperature is one of the important variables in any industrial process. Le Chatelier's principle can be used to predict the effect of temperature on the equilibrium of a reaction. You have learned that whenever a system at equilibrium is subjected to change in concentration or pressure, the reaction quotient QC no longer remains equal to the equilibrium constant Kc. However, when a system at equilibrium is subjected to change in temperature, the value of equilibrium constant Kc itself changes. For example, the equilibrium constant for the gas phase reaction of the formation of ammonia from nitrogen and hydrogen at 298 Kelvin is 6.8 multiplied by 10 to the power of 5, while it is 41 at a temperature of 400 Kelvin. The value of the equilibrium constant for a given reaction varies with temperature. In general, equilibria in which the forward reaction is exothermic, that is, where the enthalpy change is negative, have equilibrium constants that decrease with an increase in temperature. For example, the gas phase reduction of nitrogen and hydrogen combining to give ammonia. In this reaction, the forward reaction, that is, the formation of ammonia, is an exothermic reaction, and the backward reaction of ammonia dissociating into nitrogen and hydrogen is an endothermic reaction. According to Le Chatelier's principle, raising the temperature shifts the equilibrium in the direction in which the heat is absorbed. It implies that endothermic reaction is favored. So, ammonia absorbs the heat to dissociate into nitrogen and hydrogen. Hence, on increasing the temperature, the rate of backward reaction increases, or the rate constant for backward reaction, Kb, increases. You have also seen that equilibrium constant Kc is equal to Kf divided by Kb, where Kf and Kb are rate constants for forward and backward reactions respectively. As Kb increases in the denominator, the value of Kc decreases. Thus, for an exothermic reaction, the value of the equilibrium constant decreases with an increase in temperature. Equilibria in which the forward reaction is endothermic, that is, where the enthalpy change is positive, have equilibrium constants that increase with an increase in temperature. Consider the gas phase reaction of the decomposition of phosphorus pentachloride into phosphorus trichloride and chlorine. The positive enthalpy change for this reaction indicates the endothermic nature of the forward reaction. If the temperature for this reaction is raised, then the forward reaction of PCl5 dissociating into PCl3 and Cl2 occurs. As the rate of forward reaction increases, the rate constant for the forward reaction, Kf, and consequently, the value of equilibrium constant Kc also increases. Thus, for an endothermic reaction, with an increase in temperature, the value of equilibrium constant Kc also increases. The effect of temperature on equilibrium can be demonstrated using nitrogen dioxide gas. Nitrogen dioxide gas, which is brown in color, dimerizes into colorless dinitrogen tetraoxide. This dimerization, as you can see from the value of delta H, is exothermic in nature. The three identical sealed tubes that you see here contain nitrogen dioxide in equilibrium with dinitrogen tetraoxide. As you can see, all the three tubes contain the same amounts of NO2 and N2O4 and have the same brown appearance. Now, out of the three sealed tubes, one is placed in a freezing mixture, one in hot water, and one is left at room temperature. What do you observe? You can see that the tube placed in a freezing mixture has turned pale, while the one placed in hot water has turned dark brown. How do you explain this? The forward reaction of NO2 dimerizing into N2O4 is an exothermic reaction. You have seen that increasing the temperature for an exothermic reaction favors the backward reaction. Hence, the backward reaction of formation of NO2 occurs when the tube is placed in hot water. This is why you see that the brown color intensified in that tube. Lowering the temperature for an exothermic reaction favors the forward reaction. Hence, when the tube is placed in a freezing mixture, the forward reaction of NO2 dimerizing into N2O4 is favored. That is the reason why you see the tube turning pale. Now, let us look at the influence of a catalyst on equilibrium. A catalyst has no effect either on the position of equilibrium or on the equilibrium composition of a reaction mixture. However, a catalyst increases the rate of the reaction by providing a new low-energy pathway for the conversion of the reactants into products. A catalyst lowers the activation energy for the forward as well as the reverse reaction by exactly the same amount, and thus makes it easy for the reaction to proceed faster in either direction. To understand the effect of a catalyst, consider the gas phase reaction of the formation of ammonia from hydrogen and nitrogen. The formation of ammonia is an exothermic reaction and proceeds with a decrease in the number of moles. According to Le Chatelier's principle, the conditions favorable for the formation of ammonia are low temperature. Since the forward reaction is exothermic, and high pressure, as the reaction proceeds with a decrease in the number of moles. However, the conditions cannot be maintained because at low temperature, the reaction is so slow that it makes the process uneconomical. High pressure gives a high yield of ammonia, but the higher the pressure, the greater is the cost and maintenance of the equipment. Fritz Haber, a German chemist, discovered that using a catalyst consisting of iron permits lower operating temperatures and a moderate pressure. Thus, the optimum conditions for the industrial method of the synthesis of ammonia by Haber's process are a pressure of 200 atmospheres, a temperature of 725 to 775 Kelvin, and an iron catalyst to speed up the reaction. The importance of a catalyst can also be understood by its use in the manufacture of sulfuric acid by the contact process. One of the important steps in the manufacture of sulfuric acid by the contact process is the formation of sulfur trioxide from sulfur dioxide and oxygen. The forward reaction leading to the formation of sulfur trioxide is an exothermic reaction, involving a decrease in the number of moles. Thus, according to Le Chatelier's principle, low temperature and high pressure favors the formation of sulfur trioxide. However, at low temperature, the reaction is very slow, while at high pressure, the tars used in the synthesis get corroded. Hence, to maintain optimum conditions and increase the rate of the reaction, a catalyst such as platinum or vanadium pentoxide is used. The optimum conditions used for the industrial synthesis of sulfur trioxide are normal pressure, a temperature of 673 Kelvin, and a catalyst such as platinum or vanadium pentoxide. You have now reached the end of this module. In this module, you have learnt that the value of equilibrium constant depends on temperature. Equilibria in which the forward reaction is exothermic have equilibrium constants that decrease with an increase in temperature. Equilibria in which the forward reaction is endothermic have equilibrium constants that increase with an increase in temperature. A catalyst has no effect either on the position of equilibrium or on the equilibrium composition of a reaction mixture. A catalyst increases the rate of the reaction by providing a new low-energy pathway for the conversion of reactants into products. A catalyst lowers the activation energy for both forward and reverse reactions by exactly the same amount, and thus makes it easy for the reaction to go faster in either direction.